Okay, we can start, please.
Okay. Yeah, so today we have a topic of tokens and their standards, and mostly today I will talk about ERC20 token. So how does it work, and where are some problems with this standard, and etc. etc. In the next lecture, I will cover NFTs and ERC1155 standard, but today, yeah, it's like mostly about ERC20. So let's like first define and understand why do we actually need standards in Ethereum. So first of all, standards, and especially token standards, are needed to define certain properties of a smart contract for it to be able to manage and transmit value. So basically, token standards are special smart contracts that follow certain rules to be able to handle value and, for example, the transfer of value. And token standards usually arise, like as every standard, probably when developers face particular problems and they want to solve those problems in like some kind of abstract way. So they like gather together and draft a standard and then publish it in a special forum, which is Ethereum Magicians Forum. And then after that, it gets like published to Ethereum improvement proposals, GitHub. Also, using standardized contracts makes them compatible with wallets and already existing on-chain applications. So here I'm talking about ERC20 standard. So ERC20 standard was introduced like long ago. And because it is like pretty simple to understand and code, many wallets and applications have adopted it. And basically making your own ERC20 will make your contract compatible with like majority of applications. And it is important to actually search for standards first instead of developing something your own, because standards highlight and solves security aspects that are hard to support yourself. First of all, standards are drafted by like highly experienced developers, and second of all, usually standards are discussed in the like community by other developers, and a lot of attention gets into the papers. After that, like standards, if they are popular enough, get implemented in libraries. Those libraries get audited, and etc. etc. So using standards is like one of the ways to like protect yourself against some kind of attacks. So here are the probably most popular token standards out there. So of course, ERC20 standard, which is just a regular token, nothing special. ERC71 standard, which is a non-fungible token standard, or NFT, used like pretty much the same way as ERC20, except that every token can't be like changed to another token in a like similar way. So every token has its own unique value and properties. So they're non-fungible. ERC1155, which is a multi-token standard. Basically, this is a special standard that has a sort of properties of ERC20. So this standard has an array of ERC20 tokens, and in the same way, using this standard can allow you to implement NFTs, but with a limited functionality. Usually, this standard is used, for example, for tickets on concerts, where every ticket is fungible, but every ticket from a different concert is like can be changed to a different ticket from a different concert. And the standard that like suggests how to implement soulbound tokens, which is like a new type of token. And actually there is like no dedicated standard for soulbound tokens. Majority of those standards just extend ERC71 and add several functions to like identify if this token is an SBT. So one of the standards is ERC5484, which just suggests how to mint and burn NFTs. There are also several standards about soulbound tokens, but yeah, they all pretty much extend regular NFT. So yeah, today I'm talking about the ERC20. So let's take a look at what it is. ERC20 standard enables tokens to be created on chain. Basically, standard defines a certain functions, like view functions and non-view functions, or API in quotes, that can be used by third parties to interact with the token. Also, even though ERC20 standards like can be thought as like a similar to Ether, which is a native currency, Ether is a push-only asset. What I mean here is that in Ethereum, nobody can take Ether from you. Like you are the only one who can send someone Ether. So there are no like opcodes or functions to take it from you. But ERC20 standards allows you to give a permission to someone else, so that someone else could act on your behalf to transfer your tokens. This is really useful when you're interacting with smart contracts, and we'll take a look at this functionality a bit later. Yeah, actually, if you have any questions, yeah, just please ask them. This is an ERC20 interface, which I've taken from the actual Ethereum improvement proposal. So let's take a look at what we have here. First of all, ERC20 standard defines two events. The first one is transfer event, which has to be emitted every time there is a transfer of tokens. This is either a transfer from one account to another account, or for example, when someone mints tokens, or when tokens get burned, a transfer event is emitted. Also, there is an approval event. The approval is the process of giving permission to someone else to have an access to your tokens. So basically, you're allowing someone to transfer your tokens. So when this action happens, the approval event has to be emitted with those parameters. Owner is someone who gave a permission, spender is the one who received the permission, and the value is the amount of tokens which are allowed. Then there are three optional functions, but nowadays ERC20 tokens have like all of them implemented, but from the actual paper, those three are optional, so you are like not obligated to implement them. The first one is the name. Basically, you can give any name to your token, which like has like a recollection of stocks. For example, you have a project and the token is the native token of your project. So given a name of the project to this token is like one thing to do. Then there is a function called symbol. Symbol is like literally came from stocks. So this symbol basically means a ticker of your token. So it is a short, like either abbreviation or like short name of your token. It can be used to like display on the front end. If you have any like tokens, for example, in your wallet or anywhere. Then there is a function decimals. So it is a like pretty tricky function that I will also cover in the future slides. But for now, what it basically means is that it is used mostly for user interface conventions. But because in Solidity, we don't have floating point, like numbers with floating points, we only have integers. In order to present like one complete token, you can use like arbitrary number of digits in this token. So for example, Ether has 18 digits. So and one, so the smallest amount of Ether is called way, and it is like 10 to the negative 18 of Ether. So this function is used to describe which is the smallest representation of token. And if it returns 18, that basically means that the token is dividable up to the 10 to the negative 18 like token points. If this function returns 6, for example, as USDC and USDT define, then the smallest number of tokens is 10 to negative 6. But actually, this function doesn't change how the contract works. It is only needed to like define the smallest representation of the token and how to present the actual number on the front end and in your wallet. Also, there is a function total supply, which basically returns how many tokens there are in existence. Tokens can be capped, meaning that there is a hard-coded total supply that is minted when the token is deployed, and it can like the supply can never exceed this cap. Or there are tokens where the cap is not set, and like if there are certain minting permissions, someone can mint tokens and increase the supply. Then there is a function to return how many tokens the account has. Pretty straightforward. Also, the function to transfer a certain amount of tokens from yourself to the to account. So if you have any tokens, you can call this function and transfer them to the account you want. What is important here is that this function has a return value Boolean, which can be like true or false. And even though the EAP actually says that this function can return false if something bad happens, on practice, functions revert instead of returning false. But yeah, it's better to follow the standard. And if your like capacity allows, it's better to add require statements above the call of the transfer function. Because yeah, probably there are tokens somewhere in the wild that don't revert, but actually return false if something bad happens. Then there is an allowance function, which returns the allowance of the spender if owner has given the spender like any tokens to like control. And the function that actually gives this allowance, its name is approve, and basically it accepts the address of the spender that you're allowing the tokens to control and the amount of tokens you're allowing. Also, it returns false if something bad happens in the same way as transfer function works. And transfer from function, which works like in pair with an approve function, and it allows message sender to take tokens from here. Basically, if from allowed message sender to transfer tokens, then message sender can call this function, and the tokens will be subtracted from address and transferred to address, and the amount of tokens will be transferred. The same way the return argument works as to other functions. It may return false instead of reverting if something bad happens in the function. What if decimals returns 0? Is this possible situation? Yeah, this is possible. And basically, it means that token is not like divisible at all. And I think that CryptoPunks, so CryptoPunks project was implemented before the actual ERC20 was introduced. And they used ERC20 standard to represent their tokens. And I believe they have a decimals function that returns 0, which basically means that the token is not divisible at all. And yeah, meaning that only one token like exists, and you can send like half of the token. But this is like you will seldom find this in a real world contracts. Okay, so let's take a look at the implementation. I've actually taken the implementation from Soulmate, which is a popular library with like simple and bytecode optimized token implementations, because, for example, OpenZeppelin has a lot of stuff added to the token, and yeah, it's like really bulky in terms of bytecode. Soulmate is really clean here, so I will also like cleaned it up a bit for the example purposes, but yeah, it is pretty much their implementation. So we have two events defined here, the same way they are just described in the paper. Note that those two arguments are indexed. So to enable a quick filtering through events. Then there are several like storage parameters with one immutable variable. The standard says that once the decimals are set, they like shouldn't change, and they actually mustn't change. So that's why the decimals variable is set as immutable. And in the constructor, that's most variable is passed and set here, and no one will be able to change its actual value. Also, we have name and symbol here, passed in the constructor, and they are set subsequently in its body. Also note that those three variables are public, so Solidity will generate default getters for those variables, and because Solidity does so, we are compliant with the standard. We have a symbol function, name function, and decimal function. Also, there is a total supply, public variable, so there is a getter. Also, the compliance is achieved here. It is 0 by default, and there are two mappings. The first one is the mapping of user accounts and their actual balance. Its name is balance of to be compliant with the interface. And also there is a mapping of allowances. So I believe this address is the owner, this address is the spender, and this is the amount available to be spent. Also, the name is allowance to be compliant with the interface. Then there are actual functions that's like can be called with the transactions. Those three functions change the state of the contract, and these are the only functions that actually do so. Let's take a look at them. The first one is the approve function, the same interface as in the EIP. And what it basically does is that it sets the allowance to the amount. So this will be the owner. So because I'm approving something, then the message sender is the owner. The spender is what is provided to the function, and the amount. Also note that the approval event is emitted, and also true is returned. So here, if anything goes wrong, the contract reverts. But yeah, sometimes there might be cases when instead of reversing, they will just return false. Then there is a transfer function. What it basically does is that it transfers some amount of tokens from message sender to the provided to address. So here we are decrementing the balance of the message sender. If there is not enough balance, then because this contract is made so with Solidity 0.8 and above, if this line of code underflows, then there is a revert. So in that case, that means that the message sender doesn't have enough tokens to be sent. So the amount exceeds the balance of the sender. You can add like explicit require statements, but because Soulmate tried to like minimize the actual bytecode of the contract, they just rely on the Solidity compiler checks. So if this line passes, then we are certain and sure that there is enough balance in the message sender account. So we are adding the same amount to the destination account. Actually, in the original implementation, they have an unchecked block here because, yeah, nothing to check. We are already sure that the amount is correct. And note that in this implementation, it is fine to transfer tokens to yourself. You can set that to address to your own address, and then it will just like decrement and increment your balance. Also, the transfer event is emitted, and true is returned because everything is fine. And the transfer from function, which transfers tokens from and to, given you have permission to take tokens from. So this line of code checks that from has given enough tokens to the message sender, and we decrement this amount from the allowance, and the same way as in transfer, because this is solidity 8 and above, this can't underflow. The same story is here, because from has given us a permission to take their tokens. We are taking their tokens here, so decrementing from balance and incrementing the to balance. Also emitting the transfer event. So because we are transferring tokens from, the from is used as the first argument, not the message sender. And also true is returned because everything is fine unto this point. So here are the public functions from the ERC20 standard, but something is missing. Of course, the mint and burn functions are missing, and in Soulmate implementation, they are defined as internal and virtual. So because Soulmate is public library that can be used by everyone, they have to implement certain functionality, but allow the users of their library to define and extend functionality, for example, to mint tokens. So here is why the actual mint function is internal, and it is the end user responsibility to add some higher level mint functions. For example, add an external mint function, also add ownable contract, for example, from OpenZeppelin, and say that only owner is allowed to mint tokens. But yeah, here is the actual implementation of the mint function. Basically, the function accepts to whom mint tokens and how much. Total supply is incremented, and the balance of 2 is also incremented. Transfer event is also emitted, but note that when mint happens, the from address is the 0 address. Yeah, this indicates that we are minting tokens. And the same goes with the burn function, which actually takes an address from whom we want to burn tokens and the amount of tokens we want to burn. Also, it decrements the balance of mapping, and it actually checks that the amount is correct, because otherwise it will underflow. And also we are subtracting the amount from total supply. Emitting a transfer event, and in case of burn, the second parameter will be address 0. Yep. Of course, there are a lot of extensions to ERC20 tokens. For example, there are extensions that allow burning tokens for everyone, but these are off the standard a bit. And yeah, this lecture we are actually covering the actual ERC20 standard on its own. So here are the 4 offsprings of ERC20 standard, which are quite popular and can be used in the projects, if you will. So the first one is ERC777, which is an extension to ERC20 token, which adds certain hooks to it. And also it adds the usage of pseudo introspection registry contract, which is described in ERC 1820. Basically, this ERC 1820 describes how certain users can react to certain actions. And ERC777 adds certain functions to ERC20, so it extends the standard and allows, for example, to transfer tokens and call some function on the receiver. What is important here is there was an ERC777 implementation in OpenZeppelin library, but they deprecated it in the new release. So the usage of ERC777 from OpenZeppelin is discouraged. Also, there is a simple standard, but also pretty nice, is ERC1383, which basically adds certain hooks to the vanilla ERC20. It adds certain functions, so you could transfer tokens and call a certain hook or certain receive function on the destination contract. Also, you can provide some arbitrary data to that hook. Basically, this contract allows this standard allows contracts to reject certain tokens if they want. Actually, the same functionality is implemented in ERC71 and ERC1155, and there basically using those 2 standards, you aren't allowed to transfer tokens to contracts unless contracts explicitly allow that. So this standard basically adds the same functionality to ERC20. Next one is actually the huge standard, which I consider has to be implemented in every ERC20 token. It is super powerful. It is the permit standard. And permit, what it actually does is that it adds certain functionality to the vanilla ERC20 to create signed approvals. So basically, this extends the ERC20 functionality so that users could sign certain messages which are structurized and follow EAP 712 standard that typed signatures, if you remember. And they allow, and this standard allows you to sign those messages and provide the signature to the function that requires your tokens. And instead of doing 2 transactions, which are first approve, then transfer from, you can just call a function, provide the signature, and this function will go to the ERC20 contract and increase the allowance because it will verify the signature. And if the signature is correct, then the allowance will be given. So basically, it packs the 2 transactions approve and transfer from into one transaction, which is just transfer from. And because it is based on 712 standard, it is like ultra safe and replay attack resistant. Next one is a bit newer standard, ERC4626, which is a tokenized vaults sort of standard. Basically, this standard describes how to implement a contract that can hold certain tokens inside. And the standard describes how to make it correctly, how to calculate the shares and the value of the vault token. And basically, the vault token is the, like I call it the LP token, which is like a liquidity provider token. So basically, when users send something into the vault, they are given certain ERC20 token, which represents the share which those users have in this vault. And the standard describes how to correctly calculate this share and yeah, how to basically manage it. But it is also based on ERC20 standard. Yeah, and one more thing that is really important to cover today is the real-world ERC20 caveats. So working with ERC20 should be transparent because it is super simple standard, like I think hundreds of thousands tokens are deployed to Ethereum following the ERC20 standard. But still, there are several problems with that standard. The first problem is, for example, if you are implementing a contract which which collects different tokens, and you don't know which tokens it collects. For example, there is a crowdfunding something, and you're collecting donations or whatever. So you don't know in which token the donation comes. And if there is a logic that somehow calculates the total value of those donations, for example, in in US dollar, let's say, then it is super important to calculate the actual value using the decimals of the tokens, because you can't just calculate everything in like one decimal, assuming that every token has like 18 decimals. You have to somehow manage the tokens with different decimals, do some math, and then just transfer tokens considering those decimals. So you can actually do calculations in whatever precision you want, but knowing the exact decimals for every token is super important here, not to mix them up. Because, like, for example, you can have wrapped Ethereum, which has 18 decimal places, and you can have USDC, which has 6 decimal places. And having the same calculation for both of them would result that some way through the calculation, you will miss or send to the user like huge amounts of USDC because you just missed the decimals. So this is actually the sore point of Solidity developers. And yeah, always keep it in mind. Also, there is an actual problem with ERC20 standard, which is an approval front running. So I will just get back to the actual implementation of the approve function. And here you can see that the value that we are stating to the allowance mapping is the one we provided to the function. And what a malicious spender can do is that the spender can track those approve transactions. And before this transaction is accepted, they can call transfer from function. So basically, let's imagine a situation. You're given, or let's say Alice is given to Bob an approval of 50 tokens. So the transaction passes, and Bob can transfer 50 Alice tokens. And then Alice gives Bob, so she wants to increment the loans. So she creates a transaction and sets the amount to 100 tokens. What can Bob do here? Bob can search a mempool of the approve transaction, quickly send a transaction, transfer 50 tokens from Alice account somewhere, and then the approved transaction passes and sets the allowance to 100. And what basically happened is that Bob received not 100 allowance, but 150 allowance. And yeah, this is a front-running problem. There are certain ways how to mitigate it. You can just closely read an actual paper, draw references, and try to solve it yourself. But yeah, this is a problem to consider as well. The third thing is difficulties with deflationary tokens. So deflationary token is the one that inside the transfer functions, it doesn't transfer the whole amount. It reserves a percentage or a fixed number of tokens and just burns it in order to make the token deflationary. There are certain examples you can find in the wild, but the problem is a lot of protocols don't support those tokens. For example, Uniswap version 3 doesn't work with those tokens, and implementing it this way will just make your token completely unusable. And better not use this logic and implement something different. For example, have fees included into not the token itself, but somewhere else, where you could collect these fees and then once a month or once a year publicly burn those tokens to reduce the supply. But the implementation of deflationary tokens is also not really good. Also, there is a problem with USDT, which is deployed on mainnet. So why? USDT has a sort of problem with 3 functions. The first function is approve function. The approve function is in USDT contract works a bit differently. So basically, in USDT implementation, there is one more requirement inside this approve function. And the requirement says is that if there is an allowance, then in order to set new allowance, it has to be reset. So if Alice gave Bob 50 allowance and she wanted to give 100 allowance, then she would need to first set the allowance to 0. So initiating one more transaction before setting the allowance to 100. And this is a real roadblock, because working with USDT means that users either have to set the allowance to like infinity or to the power of 256 minus 1, or to always like send one more transaction that sets the allowance to 0, which is super inconvenient and breaks like pretty much everything that is left from user experience in Web3. Yeah, this is just a stupid like sort of protection. And there are problems with those two functions, like transfer function and transfer from function. Why? Because long ago, when ERC20 standard like wasn't settled, those two functions were not obligated to return the Boolean from them. And USDT actually doesn't. So transfer functions, approve functions, and transfer from functions in USDT implementation that they don't return anything. And this is a huge problem, because if you're using the high-level Solidity and you're using an OpenZeppelin interface, the calls to those functions will revert, because Solidity expects the value to be present in the return data, but the return data is empty, and the transaction just reverts without a reason. So to solve this issue, you can either remove the returns field when you're interacting with USDT, or use a low-level calls and check the return value yourself. Or you can use the safe transfer library from OpenZeppelin, which basically does low-level calls. And because of that, if you don't know which tokens you'll be working with, then it is a must to use a safe transfer library. Otherwise, there might be a DDoS problem with your smart contract. Also, there is a problem with wrapped Ether contract, which is also an ERC20 token, but it is not like a problem with the actual ERC20 part of this contract. It is a problem with the function that unwraps the Ether you're sending to. Why? Because inside, wrapped Ethereum uses, I believe, transfer a function which transfers Ether to a destination account, and it only provides 2,300 gas to the destination contract or account. That's not a problem if you are just an end user unwrapping Ethereum, but it is a problem with proxy contracts, because if the proxy contract tries to unwrap wrapped Ethereum, then wrapped Ethereum uses transfer function, forwards only 2,300 gas, and proxies might consume more gas due to the logic of delegate calls, which might exceed this cap, and the unwrapping will fail. This is also an existing problem, and yeah, either there have to be used some access lists, which are which were added in the London hard fork, or the receive functions have to be added into the proxies themselves. And one more problem that I would like to highlight is the differences between permit signatures. So even though the permit is a relatively new standard, which was finalized not so long ago, the developers also messed it up already. And there are different permit signatures or different permit type hashes used in the wild. And for example, they are different for DAI and USDC. So you won't be able to use one standard of this signature to work with those two tokens. You will have to have two different chunks of code that construct the signature completely differently, which is just a mess. And yeah, we are left with those legacy problems. Yeah, so actually this is it for today. A bit quicker than 1 hour.
Okay, thank you for a lot. We have one question in the chat. Check, please.
Which one?
The
decimals? Yeah, I have already answered.
Yeah. Okay, I'm sorry. Okay. Thank you for a lot. And thank you for all our listeners. Waiting, please, for our materials, presentation, video, and new task, maybe, I think.
Yeah, actually, new task will be available tomorrow.
Tomorrow, okay. Okay. Thank you. See you soon. Maybe we don't have question. And we can stop our recording.